the second trigonometry unit that we're looking at, and what we're going to be doing in this unit is finishing off chapter 5. It's a very, very short lesson to begin the unit. It's probably about 15 minutes, and there isn't even any assignment attached to it in terms of daily practice. And then the remainder of the unit, I believe that should be 5.4, by the way. No, that's right, 5.3. And then we're also going to finish chapter 5 tomorrow by dealing with 5.4, which connects equations and graphs. But then the bulk of the unit is chapter 6, which deals with trigonometric identities and what are called trigonometric proofs. And it's never too late to, as my mom would say, turn over a new leaf. So for those of you that have been kind of skating a little bit here and not really worrying about putting in that extra effort, I would say to you that that's going to fail you in this unit. You cannot get by in this unit by just sitting back and observing things and figuring it out on the fly. This unit requires an immense amount of practice. It really does, from my experience. I've encountered very, very few students in over 30 years of teaching this that can just observe what's going on and go, yeah, I get it, and it's just easy. And I'm not trying to frighten you. I'm trying to motivate you. It's really, and I've used this analogy before, it's like anything else. If you want to get really, really good at something, you can't just see it in action once or twice and then expect to pick up all of the nuances of it, all of the details. That's why, I'm an incredibly better teacher now than I was 30 years ago, because I've practiced. It's why somebody who plays basketball does not just, you just don't throw a 10-year-old a basketball and say, go at it, and expect them to be very good. It's why a cabinet maker, when they first start off, they're not a journeyman or a master cabinet maker. They need to practice. I mean, this is just a life lesson, really, that I'm telling you. Everything, if you want to get really good at it, you're going to have to practice. And what I'm telling you is that this is a higher level of something that requires additional practice. So when you take a look at this weighty unit, it's pretty thick. But if you were to take a look at the lessons only go up to page 19. This is the content that you're looking at, that I'm holding up, this thin section here. And a lot of the assigned problems for practice work are included in this thin section. And a lot of the assigned problems in the practice daily work are included in your textbook. This other stuff from page 20 to 70 of the handout, I think it's 70, is like extra practice. And I'm not saying that you should do everything, but I'm trying to motivate you, and I'm also trying to set your mind at ease, because in a couple of days, when we get into identities, many of you will be very confused, and that's normal. It's going to be normal. And I'll talk more and more about how we overcome that confusion. But generally speaking, I'll just throw this your way and then we can get started. You can't, at this level, look at a math problem and just stare at it. You can't. You have to try something. And I know that you've been told that for many, many years. Well, have you tried it? And I know what the student response is sometimes. Well, I don't know what to try. Well, I'm going to give you in this unit a list of about 5 things that you have to try. And I compare this to, for some reason, maybe it's in a movie. A person wakes up in a movie and they're on a road. And they're in the middle of nowhere. They don't know where they are, but they want to get home. They're not going to get home by just standing there, right? You have to take a step. You have to start moving. And you have to pick a direction. So what the person would do, if they're smart, is they'd pick a direction and they'd start moving. But what a smart person would do is, if the road got narrower and bumpier, and it started to get more bushy in the sides of the roads, and you start to hear growls coming from the bush, you'd turn around, go back to the beginning, and try something different. And I'm going to be using that analogy a lot when we talk about identities and proofs. You have to try something. You have to start walking and see what happens. And in this unit, it's very different than other math. It's not always going to be the case that you know exactly what to do. It's not always the case that I know exactly what to do. I will say to you, well, you know what? Let's try this and this and this. And it may work or it may not. And if it doesn't, we have to go back and try something different. So I'm trying to motivate you here and get everybody off on the right foot in this unit by telling you that this is going to require, for some people, a tremendous amount of effort to be successful here. And for everybody, a certain amount of effort. So we're going to be looking at trigonometry part B. And in this unit, what we're going to do, we're going to finish off Chapter 5 by looking at the tangent function as a graph, which we haven't looked at. It's a very minor detail in this course, but we have to cover it. And then the remainder of the unit is going to be looking at identities. And if you were to go to a formula sheet, what we're talking about here, and you can grab your formula sheet if you have it handy. I'll bring one up here. If you were to look at the formula sheet on the left or the right-hand side of your formula sheet, I mean, we've already learned some things. We've learned that A equals R theta, or theta equals A over R. That has to do with arc length. We've learned, you know, these statements. We understand the meaning of them, but in this unit, we're going to take that a little bit further because we're going to be referring to them as identities. And everything else, like tangent of theta equals sine of theta over cosine theta, cotangent equals cosine over sine. I'm not going to read through all of these, but you have these three statements here near the bottom of your screen, which are called Pythagorean identities. Then we have this whole slew of what are called sum and difference identities, and then we have double angle identities. All of these things which we call identities is what we're going to be working on in this unit. So that's what the bulk of this unit is about. All right, let's take a look at the first lesson. As I said, I'm going to spend maybe 15 minutes with you going through this, and then for the remainder of the time we have together, I'm going to hand back your exams so we can talk about them. And I'm also going to give you time to work on assignment number 3, which relates to the last unit. And I want to show you a quick way to work around a difficult part of that assignment. So, analyze the graph of f of x equals tan of x. You'll notice that on your unit handout it says analyze the graph of f of theta equals tan of theta. It really shouldn't matter whether we're talking about theta or x as being a variable on a graph. So we start off with this task. What does the graph of y equals tan of x look like? And we're going to use a graphing calculator. And after we're done, I'm going to explain to you the nuances of the graph and why we should really understand what the graph looks like without resorting necessarily to a graphing calculator. But, you know, ultimately, everybody, I'll just cut to the chase here. The objective is for a Math 30-1 student to be able to tell me all of these pieces of information about y equals tan of x. What is the domain? What is the range? What is the period? What are the intercepts? What are the asymptotes? What are the non-permissible values? So keep that in mind as we graph this. So I'm going to go into my graphing calculator. Not that it really matters, but I do want to be in radians because if you look at your graph, your grid there that we've got, it is set up in radians horizontally for the variable x. So I want to be in radians, and I'm just going to enter y equals tan of x. And I'm going to go zoom trig. We know, everybody, that zoom trig, we should know, sets the window settings from negative 2 pi to 2 pi. And I believe it goes, that's for x, and I believe for y it goes from negative 4 to 4. I don't know what kind of grid I prepared here. This is going from negative 3 to 3, and it's going from a little bit less than negative 2 pi to a little bit more than negative 2 pi. So if we go zoom standard, we won't get this exactly, but let's start with that and see what happens. Not zoom standard, I apologize, zoom trig. zoom trig. And we get this weird looking graph. So one of the things you need to understand is that all of the stuff that's just been drawn by the calculator is not the graph of y equals tan of x. It's drawing some things that are not part of the graph. I'm curious, and I want everybody to do this on your calculator. Do you get the same basic picture? Or better yet, let me ask, does anybody get something that is looking significantly different, like it doesn't have everything that I've drawn? And I think if you have a TI-84, you're probably seeing, this would be my guess, you are probably seeing the following. In other words, you are not seeing those vertical lines. Am I correct? Okay. Well, that's good. And I know that some of you have the TI-83. What you need to recognize that if you have the TI-83, those vertical lines are not part of the graph. It's your graphing calculator making an attempt to connect pieces of the graph. Okay. So I want to talk here before we sketch this about this location right here, which is pi over 2. And now I'm going to ask you to put your calculator in degrees because it's going to be easier for us to think of degrees here. Pi over 2 is 90 degrees, so this is pi over 2. And I would like you to take your calculator in degree mode, and I just want you to calculate the tangent of 85 degrees. And you're going to get a pretty big number. I'll do the same up here. So again, we're putting our calculator into degree mode because I want to do a few calculations in degrees. So I said tan of, did I just say 85? Okay, tangent of 85 degrees. You get quite a big number. You get 11 point something. Now, what is the reason why you're getting a number like 11 for tangent of 85 degrees? Well, if you go back to a traditional approach in trigonometry, tangent of an angle, theta, is the opposite over the adjacent, right? And you can see that at a very large angle like 85 degrees, the opposite side is growing quite big. It's gotten to be quite big, and the adjacent side is getting smaller. And as you get closer and closer to 90 degrees, that extremity, that extremeness of the opposite side growing and the adjacent side shrinking is going to become more and more evident. So if I were to take, in other words, if the tangent of 85 is 11, that means at 85 degrees the opposite side is 11 times greater than the adjacent side. And we could explain this with the unit circle, but I don't want to wade into that pool, because then we have to talk about x and y on the unit circle, and we've got x and y on this graph, and it's a mess. So what happens if I were to go to an even larger angle, like, I don't know, well, 88, tangent of 88 degrees? I get 20, almost 29. If I go tangent of 89, I'm in the 50s. Now, I can't go tangent of 90. And I'm not even going to draw a triangle with a 90-degree angle where that 85 is, because then it's no longer a triangle. I just want to throw this out and ask you to think about it. If I increase this hypotenuse, if I increase that hypotenuse, this side, the angle between it and the base, if I increase that to 90 degrees, then the adjacent side disappears. Does that make sense? There is no adjacent side. And that would mean at 90 degrees, and again, we could use the unit circle, but I think it causes added confusion. At 90 degrees, we would have tangent of theta equals opposite over adjacent. So we would have tangent of 90 equals whatever the opposite side is. That's not the point, but it would be over 0. And you can't divide by 0. So we can try this on our calculator right now. Go tangent of 90 degrees. This is something we've done before. You should see that you get an error. I don't know what it says. It might say domain error, depending on your calculator. Yeah, mine says error domain. Don't necessarily associate that word domain with what we call domain. So I cannot take the tangent of 90 degrees. What about taking the tangent of 89.9 degrees? Can I do that? Tangent of 89.9. Yes, I get this number. The tangent of the angle is really starting to take off, isn't it? It's really exploding. And those of you that are in calculus might appreciate this more than the rest of us, but there's no limit to the tangent here. It's going to approach infinity. No matter how big the angle gets, as long as you don't hit 90 degrees, the tangent is just going to keep climbing and climbing and climbing. I mean, I can go tangent of 89.99999. Now, I have a feeling at some point my calculator is going to do some rounding and it might kick back an error. But I don't think it will here. I think it's just going to give me a very large number. So as I get closer to 90 degrees on the graph, y takes off to infinity. And of course, that is what we call an asymptote. Now, they've done a very good job putting together the high school curriculum, but there's some places where we have to talk about things that you haven't really learned about in detail yet. But what an asymptote is a line, in this case it's a vertical line, that the graph will never touch, but the graph will always get closer to that line. And essentially what this is a non-permissible value. X cannot be pi over 2 radians. It can't be, because that's 90 degrees, and when you try to take the tangent of 90 degrees, you get slapped on the hand, mathematically speaking. If we extend this now, and I realize we could just draw what we're seeing on the calculator, but I want you to understand something, and I'll get back to my calculator image in a second. If we extend this now just briefly to the unit circle and start talking about tangent being y over x, at 90 degrees, x is 0, and that's why y over x is undefined. Tangent is also not defined on the unit circle at the bottom of the unit circle, because at the bottom of the unit circle, the adjacent side, or x, is also 0. And what that means is every 180 degrees after pi over 2, every pi radians, or every 180 after 90, moving in either direction, you will have a non-permissible value. So you get these asymptotes. Now, one final point before I put this together with the picture of your graph. You're in degree mode right now. Take the tangent of 0 degrees. You should understand that's 0. Because at 0 degrees, the y-coordinate is 0, and tangent is y over x on the unit circle. Go ahead and take the tangent of 180 degrees, which is over here. That's also 0, right? Because the y-coordinate is 0. So what that means is you're going to have x-intercepts at 0 and every 180 degrees. There's going to be x-intercepts. Now, don't draw anything just yet because I'm just still in explaining mode. If I were to take, you can try this, take the tangent of 5 degrees. It's going to be a pretty tiny number. Like, I would think the tangent of 5 degrees is like 0.1 or very close to 0.1. Yeah? So when we take the tangent of a small angle, we get a small tangent. As we've seen, when you get closer to 90 degrees, the tangent explodes. And what that means is that we're going to have a shape here that looks like this. And that curve is just going to keep going up and up and up and up and up and up as we get closer and closer to 90 degrees, or pi radians, which means that the graph looks like this. And this is how we draw it. We draw that dotted line, which is called an asymptote. This is a vertical. It's a funny math word, asymptote. We have a vertical asymptote. And again, everybody, I just want to make this clear. That asymptote is not part of the graph. The graph is what I've drawn in red. The asymptote is just a line telling us what the graph is doing. If we were to go in a negative direction and look at a negative angle, when we rotate in a negative direction, all of a sudden you're in quadrant 4. And in quadrant 4, tangent's negative. And what we would discover is we could do the same thing and go tangent of negative 5 degrees and negative 89 degrees, but we would discover it looks like this. And this is what the graph of tangent looks like. And this thing is going to repeat. This is going to repeat. And it's going to repeat over and over and over again. So what I've hopefully done here is explain to you why the graphing calculator spits out this image. But now I would like to just explain, because some of you might be interested in this, why on earth is my calculator giving me these vertical lines? If I can get it going. Why is it giving me these vertical? Well, I've switched modes, right? I'm in degrees. I've already gone zoom trig, so it's set it up in radians. So I'm going to go zoom trig again. I happen to be in degree mode, but I'm in zoom trig, so it's going from negative 360 to 360. This is interesting. It doesn't give me those lines when I'm in degree mode. But if I were to go into radian mode and go zoom trig, I get those lines. I think what the calculator is doing is it generates a graph by picking a value of x and calculating y and plotting it, and then moving to a next value of x and plotting the y and connecting them. So what's happening is it's getting a y coordinate here like that, it's getting a y coordinate here like that, and it's connecting them. It's drawing a line there. Yeah?
So it's not drawing a straight line?
It's not actually straight, no. It may look straight. I think I catch your drift, because if my theory is right, this line that connects those 2 points is sloped, isn't it? Has a huge negative slope. So if I'm right, I think that's what's happening. If I'm right, those lines are not vertical. I just want to check something out here. Yeah, I mean, they sure look vertical, but they're not. Okay. Yeah, they still look vertical, but they are definitely not. And again, the bigger point here, Ian, is those lines are not part of the graph. Don't make the mistake of thinking, oh, my graphing calculator is showing me the asymptotes. Those are not asymptotes. It's just a glitch in the graph. Because if you make that mistake and you have a TI-84 or higher model of the Texas Instrument family calculator, you'll wonder why the asymptotes aren't there. They're not asymptotes. Okay. So this is what the graph looks like. Let's answer the question now. What is the domain? Well, unlike sine and cosine, which repeat forever and ever, continually, they cycle up and down in both directions. This has non-permissible values. So for the domain, we have to say that x is not allowed to be those non-permissible values. So what's the first positive value of x that is not allowed? Pi. Pi over 2, rather. Pi over 2. I want to actually add that to my graph here. I wrote it originally and then I erased it. This is at pi over 2. This would be at 3 pi over 2. This would be at negative pi over 2. This would be at negative 3 pi over 2. I don't know that it's really important for you to write them in, but I would sure hope that you can look at the grid and tell me that that's what the values of x are. So how are we going to put this? Because this thing is going to repeat forever and ever and ever. There's no limit to how big x can get. It's going to keep bumping into those non-permissible values every 180 degrees. And actually, I want to go back to the graph and really highlight this for you as well. From here to here is pi radians. The distance between those non-permissible values is pi radians. So if I say that x is not allowed to be pi over 2, I have to then say x is not allowed to be pi over 2 plus any multiple of pi, or minus any multiple of pi. And we can get around the plus or minus by saying plus n pi, where n is an integer. And that means it's going to include 0, it's going to include 1, 2, negative 1, negative 2, 3, 4, 5, 6, 7, etc. Ian, did you have another question? No. Okay. What is the range? Well, unlike sine and cosine, where you have a range from negative 1 to 1 of the non-translated functions or non-transformed functions, this has a range of any real number. What is the period? How often does it take to repeat? I want you to take a look at the graph you've drawn and figure out how often it takes to repeat horizontally. Do you know?
Well,
Ian?
If it goes up infinitely, how can we say that it repeats? I mean, it does repeat, but how can
Okay, so it does repeat. How do we know visually that it does repeat? So I get your drift here. I catch what you're saying. You're saying that since each piece never technically ends, how can we say where it's going to begin again? Kind of. There's no beginning and end. But and this is, if you're in calculus, you'd gain a better appreciation of this. There's not really a limit. I'm using the word limit here in an English sense, not a math sense. There's a limit to how far it can go before it repeats. And the limit is at that asymptote. That's not a limit mathematically for you calculus people. In other words, if I were to say to you, if I take this, how far, and I picked it up off of the graph, how far would I have to move it to the left or the right to get the next piece? And the answer is pi. Right? The distance between this point and this point is pi. So if I were to move this pi radians to the right, I get that. If I were to move it pi radians to the right again, I get that. If I move it pi radians to the left, I get that. So this is repeating every pi radians. Unlike sine and cosine. So the period here, which is still given the symbol k, is pi. What is the amplitude? Well, I want you to take a look at the graph and use your knowledge of what amplitude means and see if you can figure out what the amplitude is. And hopefully you realize very quickly that you can't. Because the amplitude is defined as the distance from the middle of the graph vertically to the highest point, or the middle of the graph vertically to the lowest point. So this is not applicable. I mean, if you try to wrap your head around this thing having an amplitude, it just doesn't make sense. Now, what are the equations of the asymptotes? Well, let's take a look at the first asymptote that I talked about. There's a vertical asymptote at pi over 2. So what is the equation of this line, this vertical line? Well, it's x equals pi over 2. Because everywhere, I'm going to redraw that in green. This is x equals pi over 2. Because everywhere on that line, x equals pi over 2. So what does that mean? That means that the asymptotes can be summarized by saying x is equal to pi over 2 plus multiples of pi, where n is an element of the integer number set. And if you take a look at the domain, and you take a look at the equations of the asymptotes, there's a real subtle but important difference. The domain is saying what the allowable values of x are, and we have to exclude those values that are not allowed. So there's a not equal to. But when I talk about the equation of the asymptote, I'm talking about the equation of that vertical line. It's subtle. I don't want you to worry too much about it, but some of you might look at it and go, well, wait a minute, why does one have not equal to and the other one have equal to? And then we also have to talk about the intercepts. The y-intercept is at the origin. So the y-intercept is at 0, 0. Or I suppose we can just say the y-intercept is 0. We don't need coordinates necessarily. What about the x-intercepts? Well, the x-intercepts are at 0. There's an x-intercept at 0. And I want to just take a brief pause here and remind you, these are all things you need to know, but if you forget them, you can always graph it. I'm going to turn my axes back on. And something which I don't quite know why, I didn't know this before, but apparently if you're in degree mode on a TI-83 and you go zoom trig, you will not see the asymptotes. So if you forget any of these things that I'm telling you could be asked on an exam, not as a written response. If you forget any of them, well, there you go, you can look at them. There's an x-intercept at 0, and there's also an x-intercept at pi, and at negative pi, and at 2 pi. Any place on the unit circle, the terminal arm lands in either of these two positions that I'm indicating. And that means that we could say plus n pi, where n is an element of the integers, and we certainly don't need to put 0. One more thing that I just want to discuss. And the only reason why I'm including this number 3 is it's going to tie nicely into identities and non-permissible values of identities. Why are there non-permissible values for the function y equals tan of x? It's because when the rotation angle, this is going to get a little messy to think about, when the rotation angle x is at the top or bottom of the unit circle, the coordinates are 0, 1 and 0, -1. I don't think there's a way to explain these non-permissible values without going to the unit circle. So that's why I put this rotation angle x in quotes. I'm not saying there's something mysterious about it. I'm just saying that it's really theta, and it shouldn't be confused with this x or this x. We've learned in the previous unit that tangent of a rotation angle, I'm going to use theta here, will be y over x. So in these two places, this is how you could go about determining the value of tangent. But in both of those two locations, you have to divide by an x coordinate on the unit circle of 0. So it's non-permissible. Again, I'm giving this, I don't think it's really important today, but I'm giving this question to you because when we talk about identities, it's going to become fairly important. Okay? So, does anybody have any questions with that number 3? Okay, that went a little bit longer than I thought it would, but I purposely went maybe a little bit slower because our brains have been, myself included, maybe a little inactive over the past week or so. So what are you working on today? We don't have any practice problems. The only practice problem I could give you would be one that asks you for the domain range, all of these features of tangent of x as a graph. So I'm going to hand back your Unit 3 exam so you can take a look at it and make corrections if you need to. So a couple quick, I'm going to try to be quick here because I want to give you enough time to do these things. Please, if you want to rewrite, you need to email me. Don't just come up to me and say, I want to rewrite and I want to do it on this day. I need an email. If I don't get an email from you and we don't communicate that way, it's not going to happen. It's just that way I have a record of it and I can keep organized. So rewrites for this unit exam will be tomorrow after school or Thursday after school. Okay. Assignment number 3 is due Thursday. So I want to do one of these. Well, I don't want to do it for you, but I want to show you something. Okay. So let's say, and you can take a look at your assignment. Let's say that you're working on your assignment and you have determined somehow, and you've explained all of this, that the value of A in your equation is 15, that the value of D is 65, and the value of B is pi over 60. Okay? So let's say that you've done that, and that would be you've already completed the first bullet and you've completed 3/4 of the second bullet, and you've explained it or you've justified it or you've shown all your work. And now you're stuck with C. So you should be able to find C by plotting what the graph would look like if C is 0, and then asking yourself how you would have to shift that graph you've just drawn to get the graph you want. And I'm not going to show that to you, but by a nod of the head or a show of hands, you remember us doing that? Okay. The difficulty with that is it's very difficult to explain what you're doing on a written response. If you can do it that way, that's fine. I'm going to show you an algebraic way to find C. And the only reason why this is going to work on your assignment is because the points that you're given on your graph happen to be at max or min. If they were anywhere else, this would not work. Okay? So I'm going to tell you that on my made-up example here, the graph passes through the following point. I'm going to say that it passes through 14, 80. And it doesn't matter from your perspective whether that point happens to be a maximum or a minimum. I'm telling you that what I'm going to show you will always work if it's a maximum or a minimum. And I've never seen a diploma exam question that doesn't give you the point unless it's a max-min. Okay? So what we can do is approach this from a missing parameter standpoint. And a missing parameter means you're going to take your equation, which in this case would be a sine b bracket x minus c n bracket plus d. And you're going to start by putting in all of your parameters that you know. Right? So I would put in here a is 15. Sine of b is pi over 60. And then I have x minus c, and then I have plus d, which is 65. So this actually goes back to maybe even the third day of this course, where if you have a missing parameter, what you do is you load in the ordered pair, the value for x and y of any point that's on the graph. Ian, I thought I saw your hand go up.
Should the b value be pi over 6 or pi over 60?
It should be pi over, should be 60. Yeah. I meant to write 60 there. It should be pi over 60. Okay. So what we have learned is that in order for you to determine a missing parameter, you can go ahead and load in the coordinates of a point on the graph. Well, the point is 14, 80. Okay. So what happens if we put that in here? Well, we're going to have 80 equals 15 sine pi over 60 times x, which is 14, I think. Yep, 14 minus the thing we're trying to find, and then plus 65. And what I'm going to teach you tomorrow is that if you have an equation like this, and the best I can do for you right now is just say, like this means you've got this mess in here. What I'm going to tell you tomorrow is that if you have an equation like that, solve it graphically, but that's going to cause confusion here, and I don't want to get into that. This, let's start to rearrange this. Even though it's a mess inside, if I start to rearrange it, I'm going to have to subtract 65 from both sides, aren't I? And I'm going to show work because this is a written response question. And what I end up with is 15 equals 15 times the sine of pi over 60 times 14 minus c. And the reason this is going to work is that when you divide both sides by 15, you get sine equals 1. It's the only reason it works. And it will always give you 1 or negative 1 if you use a max or a min. So when I divide both sides by 15, what do I get? Well, I get 1 equals sine of pi over 60 times 14 minus c. So that means that the angle has to be pi over 2. If I want to solve for this angle here, I'm going to call this theta, which is really a weird thing to think about here, but theta will be equal to the inverse sine of 1. That's pi over 2. The only way sine is 1 is if you're at the top of the unit circle. So what that means is that this angle, theta, pi over 60 times 14 minus c, has to be equal to pi over 2, and you can solve that for c. The pi's cancel. If I multiply both sides by 60, I'm going to get 14 minus c equals 30. Because 60 divided by 2 is 30. I can rearrange that now for c. c will be equal to 14 minus 30. So an appropriate value of c would be negative 16. And I'm not going to spend any more class time with this, but if you were to graph this function with the a, b, the d, and this value of c, you would discover it has the period I told you, it has the amplitude, it has the vertical displacement, and it will also pass through 14, 80. Again, if you choose to find c by plotting the graph without c and then explaining how you would have to shift that graph to get the right graph, have at her. But that's a confusing thing to explain. I am recording this, so I will post the link to the video in Google Classroom sometime later today. If you need to review everything that I've explained here, feel free.